edges, and if you think of the elevation difference between the center point and one of the edges, you can get the component of the slope in the x direction. That would be, say, z0 minus z1 divided by delta. If you look at the triangle here, the first triangle comprised of 0, 1, 2, the slope in the y direction can be calculated as z1 minus z2 divided by delta. That works out easily because if you've got a plane fit through 3 points, you have effectively pinned that plane, and the x and the y coordinates are perpendicular to each other, so you don't have to worry about the x different when you're looking in the y direction and vice versa. So you've got these two, that gives the slope component in the y direction, and then you evaluate the angle with this arctangent expression, and then you have to look at which direction it goes to figure out the slope. So here I put together an example. So I've put red values here that were just some numbers I made up to sort of illustrate this point. And if you look at the values that you've got here, I've put many of the red values higher than the middle point value. So that would be, they would be discounted immediately. But the lowest value around the middle value of 45 is this value of 38. And so we're probably looking at this first triangle here from the center point 0, 1, and 2. You might have to also evaluate this other triangle of 45, 43, and 44, but the 38 is going to be lower. So I left the formulas up there, and looking at this triangle here, we've got a vector from 45 to 43, so that's a vector to the right, and it's the magnitude of the component is 0.2. 45 minus 43 divided by our cell size, which is 10. There's a y component to this vector, 43 minus 38, so that's in the straight to the north direction, of 0.5. So if you're thinking of a vector with an x and a y component, you've actually got a vector in the sort of north-east direction. Well, firstly, evaluate the arctangent of the two components. 0.5 divided by 0.2 is an angle of 68, which is effectively that angle there. And that tells us that the flow on this triangle would be going in a direction of 68 degrees. But if you look at that on that triangle, it's not outwards from the middle. It's now heading up and effectively intersecting with this 45-degree line, rather than if you started with that arrow at the center point, it would be in the second triangle, not the first one. So when that's the case, then we have to pick the slope down the steepest sort of edge, which is either the diagonal or the straight edge. In this case, it's the diagonal, this red arrow here. So you would choose the angle to be 45 degrees. You'd evaluate the slope along that 45-degree direction, 45 minus 38, 0.495. So the d-infinity flow direction in this case would be 45 degrees. The d-infinity slope would be 0.495. And that's effectively collapsed down to d8. The d8 slope would be the same value, and the d8 encoding would be whatever the encoding for that direction is. Any questions on that first example before I go to the next one?
Yeah, AJ, yeah?
No, it's clear enough.
Okay, we're good. Yes, that clarifies the issue here.
Okay. So I went through a few more examples just to make it even more clearer. So I was looking at this triangle. So now we've got the values set up so that there's a 45 and a 42 and a 43. And you can see that you're going to be in this triangle because this 43 is lower than that 44, and I made all these other values higher. So doing the same procedure, the north-south vector component is 45 minus 42 divided by 10. The east-west component is, notice the 43 is higher than the 42, so it's actually to the right. So this triangle has a component that's sloping down to the right rather than to the left, which is where it is. If you do the tan trigonometry on that, 0.1 divided by 0.3, you get 18.4 degrees. So where is that? That's over there. So again, it's not outwards from the middle. So we would identify the steepest slope along one of the edges, which would be that one. We would report the angle as 90 degrees because we measure clockwise from east, and we'd evaluate the slope as 45 minus 42 divided by 10 is 0.3. One more example, I believe. So here I came up with an example looking at a different triangle. So I think there's the 41 and the 42 are the lowest edge values. So we're focusing on that triangle. So the horizontal component is 45 minus 42. There's a component of 0.3. The vertical vector component is 42 to 41.1. Evaluate the angle within that triangle is arctangent of that 18.4. But that's an angle effectively from the westward direction. So this is, so I wanted to show this example to point out that when you're, if you're doing this by hand, you then have to think about how to calculate from the east direction when you're dealing with a triangle. It's not the first one. The direction is like that. You really want the angle all the way here, which is 180 minus this 18.4, works out to be 161.6. And then the slope is evaluated using Pythagoras theorem based on the two components, the 0.1 and the 0.3. So you guys are all going to be experts in this method after this. There was another question.
Sorry, you have a question? Can we just go back to the previous picture, David? So one of the things that I wanted to draw out of this was the red angle tells you what direction, so that's like azimuth. But the slope value there is telling you what's the slope going downhill, right? So you've got two different things going on here. You've got an angle that rotates around from the east over here, and then it gets to there and it goes, now I go down because I've got a slope on there. So there's two pieces of information. Now you could actually do an arctan on the 1.1 and 0.3 and get a declination slope as well. So when you, in the first handout that we had about the slope at the University of Texas, one of the things I got out of that when I wrote it was that you can define slope in lots of different ways. You can just say it's between this point and that point. In this instance, what we're doing is we're saying we have a point and we have two angles. One goes around like that and the other one goes down. And those two pieces of information there tell you what that is.
Okay. And that actually was part of the question that's part of this next question. Was there somebody with another question there? Or?
No, we're good.
Okay, the exercise 3 had one of the turn-ins says a table giving slope aspects, hydrologic slope, and so on. Include in your solution diagrams or sketches that define and indicate what each of these numbers means for the specific values for the cells A and B. And then the student asks, for the first part of the question, am I required to enlist the values obtained from ArcGIS regardless of the fact that it gives some wrong answers? So I'm saying yes, report the answers from ArcGIS, note if or when you believe them to be incorrect. So for example, here I've got the table here that says for the point A, these are the slope aspects, D8 slope, D8 flow direction, percentage drop, and D infinity flow direction. That you should get from ArcGIS. And this 3.33 would be different from what you did with your hand calculations. Your hand calculations should have got you to be about 4.2%. So you can say you believe this to be incorrect. The hand calculations indicate that. So effectively just explaining the story clearly. Then that student also asked, what does solution diagrams or sketches in the second part mean? Do you need to sketch that raster and show the angle direction? What I was really looking for was some sort of a drawing to show what these numbers mean. This is a slope in percentage, this is an aspect in degrees. In the solution that I prepared, I mean, I was using diagrams like this. I mean, you can depict these concepts diagrammatically, probably in many ways, and any way that sort of communicates information is okay. But for me, I was showing here that the slope and percentage is, and I guess this is actually wrong that I'm now looking at it. It should say, this should actually be percentage rather than degrees, but it's a percent down from the horizontal. So this is the vertical component of the slope, as Dr. Maidman just mentioned in the point he made previously, whereas aspect is now an angle, aspect being measured from north, so we've got north, and it's coming around to, in this case, 265, so it's almost all the way around to 270 degrees. So you can sort of depict that the aspect is that direction from north. This is a plan view, and the slope is down from the horizontal. With D8, the 3.3% is incorrect, but the value would be a percentage also down from the horizontal, and the direction of 8 is down to the southwest. So picked it like that. The D infinity percentage drop, again, the percentage drop is down from the horizontal 4.47%, and the D infinity, well, the angle 206 is counterclockwise from east, because that's how D infinity angles are measured, so it ends up giving this direction there. So you end up seeing that all of the directions are sort of more or less in the same direction. They're all in the same quadrant. They vary a little bit due to the subtleties of the methods, but there's some degree of consistency there. And the slopes are vary somewhat, 3.3, which is a little bit wrong, 4.5, and 11%. So the slope from this one is actually steeper. And if you look at the data that was involved in this, you'll see that some of the higher cells around were significantly different from the middle value, which is resulting in that. So I blanked out the ones for B, so you guys are going to have to actually do it and fill them in. Do not give it all away. And you can draw similar diagrams.
Yeah,
any questions on that?
Yeah, I wanted to add a thought here, and that is, I was asked whether everything has to be typed out or whether you can just scan and put handwritten stuff in. And, you know, and if you've typed it all out, that's wonderful, and I really appreciate that because it's clear. If you don't have time, you know, write stuff in paper, scan it, and I'll get it. It's just as long as I can read it. And what's more important is that I can understand what you did. So, for example, if you did something in a spreadsheet and you say, oh, here's my spreadsheet. Well, unless I can understand what you did in your spreadsheet, I just got, oh, okay, I guess that's right, or maybe not, I don't know. So please try to explain the logic of what you've done, not just give me some final answer to that.
And the same goes here. So hand-drawn things that are clear are perfectly fine. So I did want to just talk a little bit, maybe this next slide is a throw Esri under the bus slide, but this error, I contacted Esri about this when we first discovered it in the class in 2014. And this is the reply I got from one of, this Noah Jishnoman is, I guess, a person that's well known to David Maidman and I, and we work with him, and he's a really nice guy. Thanks very much for finding this bug for us. Yes, you are right. Our result is different. Source of the problem is not the formula. We are doing it the same way you are doing, but we implemented it differently. So the same but different. I'm not exactly sure what it means. To increase the efficiency, which led to some approximation. I apologize for the convenience. We are taking necessary steps to fix it. I'll keep you posted. Well, that was 2014. So then we were going to get you the contact. But then you can also look in the help file for this tool, and it's got some, I mean, you can read the whole thing if you like. when calculating the D8 drop raster in flat areas, the distance to diagonally adjacent cells is this, so that's the square root of 2, is approximated by 1.5. So 1.4 goes to 1.5. Now, I was trying to do some hand calculations to reconcile this, and I was not able to, by putting 1.5 instead of 1.41, get the same answer. I was unable to find a sort of consistent rule for how the answers are coming about. But there's obviously some sort of things going on. It's kind of like a government trying to legislate so that the calculations are simple, that you should do everything with pi approximated to be 3. Well, I mean, you can't just legislate away mathematical truisms.
Oh, yes,
anyway,
you can.
So that's, you can? Well, I guess we'll see. Maybe the Supreme Court will even approve that. We don't know. It's, yeah. Okay. So that's just a bit of the back story on this issue. So Esri does know about it. They've acknowledged that it's a problem. And I guess the point, I think for you guys, whenever you're using software, it's good to know what it's actually doing and that you can interpret it correctly. Maybe this doesn't matter that much. As far as I've been able to tell, the directions are always correct. It's just the percentage drop values that are not. And the directions are what we're using most of the time in watershed delineation. These percentage drop values are sort of mostly just used for illustration, and they're actually only an optional output. So, but yeah, you need to be sensitive to sort of know what it is. I guess in engineering, if you're a professional engineer, the law always holds the person responsible. You can't hide behind the software and say, I was using this software and it gave me a wrong answer. You have to verify that you are confident the software is giving you a right answer before you use it for whatever it is you're doing. So those are things you have to just sort of pay attention to. And anyway, so today we're going to get into...
hang on, before we pass on, Paras, you have a question?
We are not able to run the model.
What?
I'm not able to run the model.
What model?
Like exercise 3,
You mean the whole model or the model builder or what?
the model builder.
What did you succeed in completing it?
Yeah, the first part itself, the ASCII file to raster is not converting.
Okay, so what I've done is I just did, so the question here is how to run the model if the first tool doesn't work. And what I've done, somebody else came to ask me about that, and it worked correctly on my computer, and I just gave them the solution. So what I will do after class is I'll just post on my website the geodatabase that is created when the first step is complete. And you can just pick that and use it and forget the first step. Yeah. And so I opened the toolbox, I created the model with the first step, the one that just says ASCII to grid or whatever it is. I got it to work. I copied the geodatabase onto a file and I just gave it to him on a thumb drive. And then he was able to open that up correctly. So let's just, if you have trouble with that, then I'll just give you a workaround.
Yeah.
Yeah. Any other questions?
Can't get the PDF for today to download. Does anyone else have that trouble?
So PDF from my website's no good? Okay, so...
Explorer and it worked. I tried it on Internet Explorer and it worked, but on Chrome it did not.
Okay, oh, what can you say? If you have trouble with the same one is on Dr. Parvati's website, so you can get it from there. Okay, any other questions? I think we're good here, David.
Okay, so we're coming to Logan, and we are going to do watershed delineation based on a digital elevation model from Logan, and we're going to get data from the national map for doing that. So there's 3 parts to the exercise. First is delineating the watershed and retrieving the data, then doing the hydrologic terrain analysis, and then extracting data from the National Hydrography Dataset to work with that. So before we got started, I've just got a screenshot here from the USGS stream gauge for Logan River, which you could follow, and you can see that it reports that its latitude and longitude are those values, North American datum 1927. And if you followed the link to this, you would get to the National Water Information site, and somewhere you maybe can look at annual statistics, and you can find out what the, let's look at the discharge in cubic feet per second, and go for the, hopefully the entire period of record. There's a whole bunch of numbers, and I guess I don't know whether it gives you an average. But one of the things that we ask is that we're right at the end, we want to compare the mean annual flow that you're measuring at the gauge to the mean annual flow that the NHD Plus system is giving us. So you'll have to figure out how to get through from the USGS site here to mean annual discharge. It may involve copying all these numbers into a spreadsheet and averaging them, or poking around on the website to get mean annual discharge. Notice also that it's reporting the drainage area in square miles. That's another quantity that we'll have to pay attention to. We've worked with latitude and longitude before, and I'm asking you to put it in a spreadsheet, and to get us going along in the class, I did that first. So I've got a folder called Exercise 4, and there I've got the spreadsheet with the Logan stream, the Logan gauge data, and I've done the calculations that we've done before. The degrees, the minutes divided by 60, the seconds divided by 3,600 to get decimal degrees, longitude and decimal degrees as a negative number because we're in the Western Hemisphere. So the first thing we want to do is put that on a map. So the first thing I actually have to do is sign into ArcGIS Pro. Golly. I hope I've got my password right. Apparently, second time is a charm. So I'm going to open a standard map project. I'm going to put it into, well, I happen to create this folder in the downloads folder, so I'm going to say that's the folder, and I'm going to call it Exercise 4. We're going to, let me close the Excel so that we don't have two computer programs trying to work at once. I'm going to go through the process of adding data and going into wherever that spreadsheet is. So I can, it shows me the sheet. I say, okay, and I get this table here that I can look at, and it's just the values that I saw previously in the spreadsheet. But to put it on the map, we go through no, I didn't want to do that. Okay. I still need to create the geoprocessing cache. Let me, while I'm doing that, close this table.
David, what is a geoprocessing cache?
Who knows?
Okay.
I'm going to guess it's the software caching a lot of the programs it's going to work with locally. And the first time you open ArcGIS, it does that. The problem in this classroom is that when I log out, it wipes the computer and it comes back fresh every time. So it thinks I've got a new installation, and it sort of does that every time. So you can ask your Esri friends what the geoprocessing cache is. It sounds like geocaching, maybe.
Yeah, so the word cache means make a live local copy of something that you would otherwise access from a disk. Have I got that right?
More or less.
Yeah.
I guess we live in Cache Valley, and that's where they used to cache beaver pelts in the early explorer days. Mm-hmm. That's where the valley got its name from. The trappers used to catch a lot of beaver here. Mm. So I wanted to display XY data, and then it brings me into this XY table to point tool, and I just have to specify the fields to be the decimal degree fields that I want. X is longitude, Y is latitude. Make sure I get them the right way around. And here you actually have to pay attention. It's got coordinate system WGS 1984. We noted on the USGS webpage that it was North American datum of 1927. So if you want to actually care about getting the right answers, which given my lecture about being good engineers, we should, we now need to go and find the North American and USA and Territories NAD 27 coordinate system and run it with that. So now we get, we show where we can see where the dot is on the map. We can zoom in a little bit to get familiar with where we are in Logan. I found it actually seems to be better to change the base map from whatever the system opens as a default to the topographic version, because that's then when you sort of zoom in close, it shows the sort of contours. So now we've got, this is the, that's where the stream gauge is, just near the mouth of Logan Canyon, and Utah State University is just over there. So we're going to be delineating the watershed, and we're going to use the tools that we've used before. So I actually have to go and sure that the tools are available. I go to Portal here, ready to use tools, the hydrology ones, watershed. Previously, when I was doing this, we were just clicking to pick points on the map. Here I'm actually going to choose the point that we got from displaying from our table. And I'm going to go with the finest resolution data, because that seems like a good idea. And run this tool. So this will get you a sense of where the Logan watershed is. And we can sort of, well, let me just let me go zoom to layer. So you can see where it is. You can see that there's this canyon up here, and Bear Lake is not that far away. And we could actually re-symbolize this to be something perhaps transparent. And let me actually put the outline color as maybe the green that we always seem to be using for this. And let me put a very light color in for the watershed. And one of the things that you can actually also do is make these layers transparent. So if you go to Appearance and drag the slider bar, you can sort of get a sort of transparency effect there. This tells you where the watershed is, and I wanted you to be aware of that, because now we're going to get digital elevation model data for this area. And rather than doing it from the Living Atlas, which we did for the previous exercise, I'm going to show you how to get it from the national map. A number of reasons for that. We discovered in last class that Living Atlas was actually down, or it wasn't discovering these things while we were searching it. It seemed to rectify itself a little bit later, so sometimes things aren't available. The best data we can get from the Living Atlas seem to be 30-meter resolution. From the national map, you can get 10-meter resolution data. And sometimes it's good to go to an authoritative source. So I'm going to go down here and find the national map. So I can go to the national map viewer, and I know right away that I'm going to be downloading data, so I'm going to go straight away to the data download, and I'm going to zoom into northern Utah. Get zoomed in around here, and I'm going to be getting elevation products. So you can actually read about them all, but the elevation 3D elevation program will then show me that there is 1/3 arcsecond DEM. So one of the calculations that we'd actually be doing is what is the size of a grid cell with 1/3 of an arcsecond, and it's roughly 10 meters. So I'm going to find where those products are. So now it's actually doing a search based on the map display. You can see it. You can either search with current extension, or you can specify various points. So it's listed me a number of things it's found, and I need to figure out which are the ones that I actually want. You can actually click on this footprint link, and now it'll show you the blue link. So we see that part of, we remember the Logan watershed went from Logan, it kind of went up here, and it actually extended into above this 42-degree latitude line, which is the border between Utah and Idaho. And so we're going to get part of this one, but we may need to be a little bit further north. Look at the footprint of that. That's off to the west. I don't want that one. This one is off to the east. This one is the one immediately to the north. So I'm actually going to want both of those tiles. This data is delivered in 1-degree tiles. You can sort of zoom out and see those are the areas. So I'm going to actually download that one and save the file.
At this moment, even though these are 1 by 1 degree tiles, they look rectangular because by the time you get this far north, the meridians are starting to come in together, so that the long distance is longer than what the width distance is, as you can see in this picture here.
So there, I downloaded the first one. I download the second one, and you can see the downloads are happening fairly quickly in Firefox, thankfully. And in the downloads folder, these are the zip files that I've just downloaded. So let me extract all the data from them. So I'm going to extract that one and extract the second one. You'll see that these zip files actually extract into folders that have the names and so this is the naming basically says this is a USGS National Elevation Dataset. I believe the 13 means it's probably the 13th version, so there'll be a new version. N42W112, that's the northwest, that's 42 degrees north, 112 degrees west, and that's the northwest corner of those particular tiles. If you look inside these folders, you see that there's an info folder, and there's various other bits and pieces that are the data associated with an Esri grid format data set. You'll see that the format there was arc grid. We could have chosen to search for the data in a different format. Here we had the file format arc grid. If we wanted an IMG format or one of the other formats, we could have chosen there. But arc grid was the default, so that's why I got that. So now I'm going to add this data to my map. So let's go. Okay, before I do that, I'm going to actually put those folders inside my exercise 4 folder. So let's put those there to keep it all together. And go to my exercise 4 folder, refresh this. Sometimes you have to refresh it to see what's there, and go into each one of them. Now you don't actually see quite as many things because it's showing you a raster data set. There's many files that comprise a raster data set. So I'm just going to load the first one, And something happening here. Yeah, the wheels are spinning. There we go. So there you can see I got the southern one that sort of chops off just a little bit below the watershed boundary. And if I add the second one, I should get the part immediately to the north. So now I've actually got two grids that have been loaded onto my map. I really only want to work with one of them. So what I'm actually going to have to do is I'm going to have to do some work to merge these together, and then I'm going to have to do some work to clip them out just for the area that I want with a little bit of a buffer. So I think that the trick to merging these is to know what the tool is called, and it's called Mosaic. Who would have thought? I guess it's Mosaic to new raster. So if you read about that, it says merges multiple raster datasets into a new raster dataset. So we open this Mosaic tool. We can choose that our input rasters are the two that we've got. And the output location, let's choose it to go into the exercise 4 geodatabase that was created when we created the project. Let's call it Urge DEM as the data set. And I happen to know that this is a 32-bit float. If you were uncertain as to what to put there, you could actually look at the properties of these rasters that you're merging to pick something consistent. I also happen to know that there is one band. You could also see that in the properties there. And I've got screenshots of the properties in the exercise to do that. So now I'm ready to run this, and we'll get this. We should get a new raster added to the map that is the merge of the two of them. It's actually quite a big data set, so this may take a while, but thankfully the computers are getting a lot faster. Years ago, we wouldn't have even tried this because it would take too long, but software's gotten better and computers have got faster, and now we can do it. Although maybe it's eating up my time. There we go. So the next thing I'll be doing is I want to clip it out according to the boundary of our basin here. But I actually am going to have to do some coordinate system work first, because I want to work with a consistent projected coordinate system. If you do these raster calculations in geographic coordinates, which is what this data is, you don't end up calculating the slopes correctly, because the horizontal dimension is degrees, the vertical dimension is meters, and the ratio of those two doesn't give you a meaningful slope. So the first thing I'm going to actually have to do, and I think this is on page 13, is create for myself a feature data set in a coordinate system that I want to work with. So I think that this system actually lets you do multiple things at once. So I'm going to leave that running and go to my databases here, and in this exercise 4 geodatabase, say I want to create a new feature data set, and I'm going to name this base map, as we've been commonly doing it. If you look at where it is, it should, and then I need to pick a coordinate system for this. I decided, more or less arbitrarily, but just to mix things up, to use the UTM coordinate system for this area. So we might have remembered from our earlier work that we're in UTM zone 12. So I'm going to go to projected coordinate systems and find UTM. Let's use North American datum 1983, pick zone 12, and there we have, so now I'm set up to effectively create this base map feature data set in this geodatabase as soon as I run this. Notice while I was doing that, this mosaic to new raster completed successfully. The merged DEM is there. I could actually remove these other ones from my display. I think the instructions actually say to remove them later on, but I've effectively got one large digital elevation model that covers this area. So do I have a, I think I have something for you to hand in here to figure out what the cell length in north, south, and east, west is for this merged DEM. So if you look at its properties, you'll see that if you look at the raster information, it's 10,000 columns, 21,000 rows. The cell size looks perhaps a little bit off-putting initially, 9.259 times 10 to the minus 5. What does that actually mean?
What are the units here?
So what are the units? Does anybody know what the units are? It's decimal degrees. So this is 0.0000409259 degrees. So for this thing that I've asked you to turn in the cell length in meters, and I've said that so assume the Earth is spherical, and I gave its radius. You can then go to the calculations we've done and do the north-south calculation, the east-west calculation, and then figure out the area as the product of those two. And that way, that'll reinforce the idea that you'll see that you'll see the sort of north-south, east-west effect that we got there before. I'm going to run this command to create my my feature data set, and it's completed successfully. So if I went to the catalog and looked inside my geodatabase, I can see that there's this base map feature data set. There's a few other things that are here already. Notice feature set 1 and feature set 2. Those correspond to the output watershed and the output snapped points. And it's kind of interesting. If you look at one of these layers, its properties, you'll see that it says it's a feature class feature set 1, but if you look at the general part, it's got a name output snapped points. So the name displayed here is something more interpretable, but what's in the geodatabase is just called somewhat obscurely feature set. So you have to just sort of be aware of those differences. And our merged DM is also there, as well as our feature class from the table. I'm going to take these data and put it inside my base map, because that'll effectively serve to project it. So the first one I'm going to do that is with my the gauge that I put there. So I'm going to go to export that, and I'm going to choose where I put that inside this exercise 4 geodatabase base map. I'm just going to call it gauge, and now if I run that, you'll get it's now appeared inside this base map, and it'll be in the UTM coordinates. I'm going to do the same thing for the watershed. So let's, I guess, go to data, export features, gets me back to the tool, and I'm going to call this basin, and run that. So now the gauge and the basin that we got added here. I'm going to get rid of these earlier ones to keep things simple. So don't need that, don't need that. Don't even actually need that anymore. Maybe I'll put the gauge, something that I just happen to like to use, these circles with a dot in them for stream gauges, and I always like them to be green. I don't know whether that's a useful convention or not. And let's have this basin be sort of a bigger boundary with the light green, and we could make it transparent again if we want. To clip out our digital elevation model, we want to account for the fact that there may be an area around the edge that is that flow may come from, so it's useful to use a buffer. So I'm going to find whatever tools there are in ArcGIS for doing buffering. So let's go to open another tool, find buffer. We've done this before. So the input feature is going to be my basin. Let's put the output feature class, and I'm just going to call it basin buffer in the same feature data set. And I'm going to go with 1 kilometer. And I think the defaults are, the rest of the defaults are just fine. So now you can see that it's a little bit bigger than the one we had before. It may be hard to see until I zoom in. You can see it's sort of, it's, that's about 1 kilometer buffer that we've got around the edge. So now with that, and I guess I call this merged DEM, and in the exercise I called it DEM merged, but we can figure that out. I'm going to extract the DEM just for the area that's within our buffer. So I'm going to again find the tools and look for extract. Extract by mask is the spatial analyst tool that says extracts the cells of a raster that correspond to the areas defined by a mask. So I'm going to choose my merge DEM, and I'm going to say that it's going to the basin buffer, and the output raster, I can't put a raster in a feature data set, so I have to put it at the top level database, and I'm going to call it DEM, and I'm going to put GC to remind myself that this is actually in geographic coordinates. Later on we're going to have to project that to our UTM coordinates. So let's save that, run that extract tool, and now we can look at, if I turn this one off, you'll see that we've got a DEM that just covers the area of our watershed. So we're starting to make progress to be able to do our study, but it's still in geographic coordinates, so I need to put it into projected coordinates, and the tool for that is project, and it's the raster version of that. So let's say the input raster is this geographic coordinates, the output raster, I'm just going to call it DEM, and the output coordinate system, I'm going to choose the same as the things that are in my feature data set, gauge, and you'll notice it then picks the UTM coordinate system. I'm going to use the transformation of cubic convolution because that retains some degree of smoothness. And it's picking for me a default cell size that's 8.9 meters. So that's some sort of a average of the north, south, and the east-west directions. So when you're doing that calculation, you know that you should have got an answer that's close to 8.9. The east-west will be less, the north-south will be more. I'm going to actually just change these to 10 because I want to work with an exact integer meter cell size rather than 8.9 whatever. I could have put a 1 there and I would have got a really fine resolution DEM. That wouldn't be really justified because the data is coarser than that. So if somebody tells you they've got a high resolution DEM, you have to actually think of what was the resolution of the source data that it came from. But here I've now projected the digital elevation model. Notice that the upper and lower bounds are slightly different than the original one, and that's because the data was actually changed. The process of projecting the data is doing resampling because the grid cells don't perfectly align. We don't see any of the effect at this scale here. It still looks like it covers the area. So you can look at the property.
Comment here. You chose the UTM coordinate system. Maybe you wonder, well, why UTM coordinate system? One of the reasons is that that's the coordinate system used for search and rescue. So if there's any rescues that have to be done in this area, they say helicopter go there, airplane go there. Always the coordinates are given in UTM coordinates. So there's sort of an operational reason for emergency response for using this coordinate system.
Okay. So I haven't saved this project yet, so probably I should, just crashes. I think we're at the point where we've now extracted a lot of the data that we want, and I've given myself just about 20 minutes left of class to do the watershed delineation. It would be better to, maybe I should have started with all the data ready to go and done the cool stuff, spend more time on that. Anyway, I think it's fairly straightforward. We're at page 20 if you're following along. I'm going to remove some of the things that we don't need, the geographic coordinate system and the merged DEM. I'm also going to change the map projection. So if you go to the map, this entry here in the table of contents is referred to as a data frame, and it's effectively holding all of these layers, and it itself has a projection, and that's what everything in the map is projected with. So if I go to its properties and coordinate systems, you'll see right now it says North American datum 1927, and that's because the very first data that we added was in that projection, the XY coordinates we got from the US spring gauge. I would rather use, somehow it associates that with Canada, I would rather use one of the systems that's associated with one of our layers. So I'm going to expand the layers, and I'm going to go to the North American datum UTM zone 12. And watch what happens when I click here. Look at how fat the watershed is, and we suddenly get a little bit skinnier. So that's because it's now depicting it in more the sort of true projection. The previous one was geographic, and the east-west and north-south distances aren't quite the same. So for your diet plan, all you have to do is go to...
That's what I'm saying, yes. Project yourself to TM. You'll get the body you always wanted.
So now we're going to go through the sequence that will be well rehearsed by the time you have done this. Fill the sinks, calculate flow directions, do the flow accumulation, and so on to delineate watersheds. So I'm going to go back to my geoprocessing tools, and find the tool for filling. And it's part of Spatial Analyst. It actually makes a difference whether you click on the tool or the tool set. If you click on the tool set, it'll open you the tool set, and that's going to be handy because I'm going to use some of these other ones. So let me click on Fill, and I'm going to choose this DEM, and I'm just going to name the results Fill, I believe. And I'm going to run this tool. So now it's doing the process of filling the sinks for this digital elevation model. While it's running, I'm just going to switch back to the exercise and show you what comes next, and skip over a few things to move us along. You'll see that at this point in the exercise, after the fill has been done, I go through a calculation of doing the fill minus the original DEM, and that gives you a raster that you can then look for where there's sinks. And one of the sinks up in Logan Canyon is actually well known. It's called Peter Sink. It's a real topographic feature about 60 meters below the highest pour point, so it's internally draining. And it's one of the coldest places in the world. And you can go to its website and you can see that on this day in 2010, it was minus 46 degrees Fahrenheit. And that's because the air just drains in there. So you guys can sort of explore that by itself, but I'm going to just move on and calculate the flow direction and do the watershed delineation. So I can go back, and in my spatial, in my hydrology toolset flow direction, the input surface raster is going to be fill. The output flow direction raster is, I just always call it FDR, flow direction, or Franklin Delano Roosevelt. The drop raster, I'm going to call DRP. These are the values that will be slightly incorrect because of the square root of 2 is 1.5. And we're using the D8 approach. And that's because we're going to delineate watersheds where our channels aren't going to diverge. It just goes from one grid cell to the other. So we run that through. And this may take a little bit of time too. So there we have the the drop values range from almost 0 up to 710%. So what would 710% mean?
That's a very steep drop.
Very steep. So if you've been to Logan, you'll notice there's a canyon here where there's some cliffs, and it's effectively saying you move 10 meters horizontally, you go 7,000 meters vertically. So I guess it's probably there are places where there's no 71. It's percentage. So it's 10 meters horizontally will be 7 times that vertically. So 70 meters vertically. So there's cliffs that are easily 70 meters up the canyon. You can also see the flow direction values, and let's zoom in a little bit to see. So you can see the values of the encodings 1, 2, 4 through 128, and you can click on any one of them, and you find that the flow direction for that is actually a value of 4. So now you remember the encoding is 1, 2, 4. So at that place I click the water is flowing south. Once we've got that, we can calculate the flow accumulation. So I'm going to use the flow accumulation tool and with a flow direction raster as input, I'm going to just use FAC, and I'm going to say the output data type I want to be integer. It's just counting the number of grid cells, and it's doing the D8 flow accumulation. And is that going in the right place? Yes. So run that. So now it's effectively going through the process that we showed on the slides of counting how many grid cells drain into every grid cell. This is probably the slowest running of the tools that we've got, because it's actually got to, information's got to propagate all the way from the watershed way up to the downstream end. So it's you can't evaluate the results at the downstream end until you've evaluated the results that it flows into. So I'm not sure exactly how long this is going to take, but hopefully not too long. And I'm not quite sure how to interpret these percentages here, because it seems to stick at percentage 3% for a long time, and then suddenly it's done. So it's actually not very, very helpful in terms of progress. But let's give a little bit of, let's switch back here to the handout while that's chugging along. After we've calculated flow accumulation, there's instructions here for symbolizing it. The numbers of flow accumulation get really large, because here we're dealing with 10-meter cells, and you can get the area will be the number. The area of Logan watershed is going to be hundreds of square kilometers, which is going to be hundreds of thousands of grid cells. I also show here that it's usually helpful to symbolize it with a sort of a multiplicative scale. It sort of goes 30 times roughly 3 to 100 times roughly 5 to 5,000 times roughly 4 to 2,000. So while I was talking there, the flow accumulation finished. So let me go and adjust the symbology. And I'm going to, rather than have a stretch, go with classified, and I'm going to go with a sort of a blue color scheme, because flow accumulation is kind of aligned with water. Where is the one that I like to use? Okay, let's go with this one. So, and then you can actually, rather than having natural breaks, let me go with a manual interval. So now I can enter the values I want. So if I say the upper value is 30 grid cells, 100 grid cells, 500 grid cells, 2,000 grid cells, and it seems to be applying it automatically. So now you can see that all the light blue cells are where there's less than 30 cells draining into each grid cell. But you can see you start seeing the drainage patterns, and the drainage patterns are indicated by these large numbers. And if you zoom in right near the outlet, you'll see that at the 10-meter resolution of the digital elevation model we're working with, the gauge location is not referenced exactly on the DEM. So these are some of the things you have to deal with when you sort of get really precise. Some of these latitude and longitude coordinates came from sort of early survey work. Also, you'll notice that the watershed boundary that we got from the watershed delineation tool is dealing with bigger grid cells than the 10-meter DEM data that we're working with. So I think it was dealing with 30-meter DEMs, and it's also skewed off to the side. It was actually using a national coordinate system, not the sort of local coordinate system for this area. So I can click on that cell, and let me actually go to the this explore thing, they show me all visible layers, and click again, and expand down. And I'm seeing my flow accumulation is 558,000, 5 million grid cells. Times 10 meters, times 10 meters, you'll get 500 million square meters, which is about 500 square kilometers. You might also be able to look at the attribute table of our basin, and you see its shape area is somewhat consistent, 500,000 square meters, or 555,000 square meters, so you could convert that to kilometers. So I think I've asked you to examine the basin area as well. And remember, we looked at the USGS site, and it was 214 square miles. Do the mile to kilometer conversion, and those numbers should all be reasonably close. So I'm hoping that you'll sort of see that everything is hanging together reasonably well.
David, before you
Let
pass
me
off
also
this,
show you.
before you
Go
pass
ahead.
off this, could you just do something, make an inquiry here? So could you just go into a tributary and show the flow accumulation, then what happens when it gets into the main channel?
Okay, so if I click there, that's on a tributary, I'm getting flow accumulation of 105. If I click there, I've got a flow accumulation of 557,739. If I click there, it's 557,337. Let me click one back. So there's a 218,329. So it increased about 100 going from there to there, and what was coming in was 105. So if we go to a bigger tributary with a darker color, it might be more illustrative. So this one, there's 899, nearly 900 grid cells flowing in. There's a value there, 7,098, and there it's 7,111. There it's 6,195. So we would infer from those numbers that we just looked at, well, what would we infer? Does this grid cell go diagonally into the stream or straight down into the stream?
Depends on the flow.
Does anybody remember the numbers? Sure. So we could look at the flow direction. So what is the flow direction is 16. Well, let's click there and see what the flow direction is. Flow direction is 4, so it's actually going straight down. So we would expect this grid cell includes this area, but this grid cell immediately to the right does not. So there it's 6195, here it's 7098. So it's increased by about 100 well, it's increased by, it looks like 106 or 7, and what would I get? It's increased 195 to 098. It's increased by about 903, of which 899 came from here. So there may be some other, maybe this cell flows there, that cell flows there, and so on. There's a few other cells coming in.
Yeah, the reason why I asked Dr. Tarberton to do that is that when I first started doing this work, and you sort of click on these things and you suddenly see, here's this stream and it's got this huge number of cells that flow into it, and it's an extremely methodical method. I mean, it's amazing how systematic you can be. Just like a simple rule applied repetitively over thousands and thousands of cells gives you this very evocative demonstration of just how much area is upstream of that point. In 2013, we had a flood here in Onion Creek, and the people who were in the fire department who were on Onion Creek, they just see the creek. They didn't see the fact that there's an area upstream which is as large as the city of Austin. It's out there in western Travis County and in Hayes County. And out of the midnight hours, that upstream area delivered a big flood down into the lower area. 5 o'clock in the morning, there were 700 houses flooded and 5 people were drowned, and there was no warning at all. And that's sort of the power, that big purple line there can really deliver a punch. And it did. This capacity to be able to quickly understand, how large is the drainage area above a place is really, really critical. We have a Texas medical center in Houston that got flooded in Tropical Storm Allison, just millions and millions of dollars in damage. And we've got a medical center being built here in Austin. And you think, oh wow, right next to a creek. But when you look upstream, there's only a small drainage area there. The medical center in Houston drains from way out in the western area of Houston. So the sort of the flow accumulation really matters here when you think about locations and flood risk and what's next to these rivers.
So I zoomed out, and you can see, so this whole area here, which is, well, we'll figure out in a minute how long it actually is, but this whole area is draining through those individual grid cells that you can track with the flow accumulation. So the procedure for mapping streams from flow accumulation is to apply a threshold. So here I'm going to go back into geoprocessing, and in the map algebra raster calculator tool, I'm going to just say flow accumulation to be greater than, and now here you have to pick a number, and this is where all the choices of stream drops and the stuff we spoke about last time comes into the choice. I'm just going to go with 50,000 because I know that works reasonably well here by trial and error, and I'm going to put this in my geodatabase, and I'm going to call that STR for streams. So we run that. If you look carefully, you can see there's a few little blue spots of streams. To see what's going on, you really have to sort of zoom in there. You can see you've suddenly mapped what looked like streams going down the watershed. If we change the zero values to be transparent, so maybe make that no color, did that work? No, I guess I have to change that value to be no color, and turn off the underneath ones. You can actually, I want to turn off it. You can see where now my blue streams are sort of lining up with the topographic contours of the base map. There's a blue stream coming down Spring Hollow, so I've been hiking and running up Spring Hollow, Mill Hollow. This is Third Dam, for those of you who are familiar with Logan Canyon. And you can see the blue streams are mapped. Yeah, the streams are just from this DEM. It's been mapped following along where the river is. So there's a little bit of an issue going on. We want everything to stop right at our outlet here. We don't want to continue all the way down to our buffer. So I've got a step here to effectively clip that raster by our basin boundary before I do the next step of processing into streams. So I'm going to go with the clip tool and extract input features. I guess the data management one cuts out part of a raster, so there's multiple clips. The input raster is going to be the streams. Is this the right tool?
Why wouldn't you just...
No, it's extract.
Do the watershed
it's extract by
and then
Mars.
extract from that. At this point, if you do the watershed function, you'd get a watershed from the green point.
Well, but that's what I'm going to use the basin that I got from the watershed to do that.
Ah, okay.
So, but I'm going to. It's not actually clip; it's extract. And the terminology between clip and extract is a little bit tricky to keep straight. So I'm going to do that. So here the raster is the basin. So this was what I got from my watershed function effectively. And the output is going to be, I'm just going to call it STR clip, and we can run this, and now we will get effectively, so if we zoom back to that layer,